Unit 1, Lesson 1, The Scientific Revolution. Unit 1, Lesson 1, Vocabulary. So what was the scientific revolution? The scientific revolution is generally viewed as a 17th century phenomenon. Most historians consider it to have started with the astronomical discoveries of individuals like Kepler and Galileo and ended with the publication of Newton's major works. We'll describe these events as bookends of the scientific revolution in greater detail throughout this presentation. Science before the scientific revolution was based almost entirely on reasoning. More than anything else, science, we should know, is a habit of mind. It involves using reason, observation, testing, and systematic thought to uncover truths about the world and about people, animals, and things in the world. Science as we know it today didn't really exist before the scientific revolution. Instead, scientists in ancient and medieval times were really philosophers who drew conclusions based on deductive reasoning. They rarely conducted practical, physical experiments. Much of what was considered science in medieval times had very little basis in fact and drew more from superstition and religious belief. Similar in many ways to chemistry, alchemy aimed to develop potions that would do things such as change iron into gold, or cure all disease, or bestow immortality to mankind. Astrology itself was based on the concept that the positions and conditions of celestial bodies, other objects in the sky, could influence human existence, both positively and negatively. Practitioners of astrology would often claim that human suffering, including sickness, could be explained by the position of the stars and other celestial objects. So, what factors led to the scientific revolution? Well, a number of factors helped lay the groundwork for the scientific revolution. First among them were the rise of colleges and universities. The first universities appeared during the Middle Ages. Although universities initially focused primarily on topics like law and philosophy, they gradually expanded their offerings and came to establish professorships in areas such as mathematics, astronomy, medicine, and other science-related disciplines. Universities helped bring together leading scientific minds and encouraged intellectual debate and sparked an interest in research and discovery. Also helping these factors was contact with non-Western societies. Muslim scholars of the Middle Ages made several important mathematical and scientific discoveries. During the 12th and 13th centuries, for example, both the Crusades and the expansion of trade networks brought Europeans into greater contact with Muslim societies. Both cultural and intellectual exchanges occurred. This infusion of new ideas helped improve Europeans' understanding of mathematical principles in particular and of science in general. As the Renaissance dawned and inspired advances in art and literature, educated Europeans began to look beyond the church and the Bible for knowledge and truth. In addition to serving as patrons of the arts, wealthy families such as the Medicis in Italy also supported scientific research. This led to an age of exploration and proved important for the scientific revolution, as the challenges of navigating across the Atlantic Ocean and around Africa motivated advances in mathematics, astronomy, and cartography. European monarchs interested in expanding their overseas empires provided funding and or support for the scientific research. Pictured before you is renowned thinker and philosopher and mathematician Rene Descartes. The philosophy of rationalism holds that all knowledge comes from reason, and that reason, not tradition, is that source of all knowledge. Many regard Descartes as the father of modern rationalism. In both Discourse on Method and the Meditations, he reasoned that all of his prior knowledge was subject to doubt because it was based on traditional beliefs rather than on reason. And he wondered to himself how he could honestly say that what he knew was true was actually true. He went as far as to doubt whether he was awake or in a state of dreaming, or if he even existed. So Descartes, the French philosopher and mathematician, is most known for a process called deductive reasoning. summed up by the Latin phrase cogito ergo sum. I think, therefore I am. This helped Descartes draw a clear distinction between mind and matter, an idea that helped break down superstitions that had influenced science in the medieval era before. Contrary to rationalism, empiricism is a belief that experience is the only true source of knowledge. That is to say, you gain knowledge through observations. Empiricism stands in opposition to rationalism, which held that knowledge could be acquired through the exercise of one's reason alone. Some of the first writings on empiricism came in the 13th century from Roger Bacon, an English scholar. He wrote that there are two modes of knowledge, through argument and experience. Argument brings conclusions and compels us to concede them, but it does not cause certainty nor remove doubt in order that the mind may remain at rest in truth, unless this is provided by experience. Empiricism helped lead to the development of the scientific method, which is still the preferred method for logic-based and reason-based conclusions now in the 23rd century, 21st century. English philosopher Sir Francis Bacon laid the theoretical groundwork for what became known as the scientific method. His ideas about science incorporated what is known as inductive reasoning, which involves using concrete facts to extrapolate broader conclusions. Inductive reasoning is the opposite of deductive reasoning. Bacon argued that scientists should work from the specific data to the general rules and theories based on that data. He believed that all scientific research should rely on careful observation and experimentation rather than simply relying on one's own thought and reasoning. This is what earlier scientific thinkers had done. The data obtained should then be recorded and analyzed according to logic and reason, then used to produce a testable hypothesis. This method is still in use today. That scientific method can be broken down as follows in this multi-step process of observing an object or a phenomenon, developing a theory that explains the object or phenomenon, and then testing that theory with experiments and coming up with data to help form conclusions. The roots of scientific thought begin sometime around the 4th century BCE with Greek philosopher and scientist Aristotle, who wrote several scientific works based on reason and logic and not empirical evidence. His work laid the foundation for scientific study through the medieval era. Aristotle helped pioneer the theories of gravity and the theory of falling objects, and helped provide some of the first glimpses of astronomy, of these crystal-like spheres that objected and rotated around. Aristotle came up with many brilliant insights into philosophy and government throughout his time. His theory of astronomy, which hypothesized that a motionless Earth lay at the center of the universe surrounded by concentric crystal spheres. One sphere held the moon, another the sun, others held each of the 5 known planets at the time, and the last held what the ancient Greeks referred to as fixed stars in the sky. Ptolemy, on the other hand, was a 2nd century Greek astronomer, mathematician, and geographer. He was a very influential mathematician. He wrote his work, also known as the Syntaxis, was the Almagest. This was his most important work. In it, he provided a comprehensive overview of mathematical astronomy and formalized the concept of a geocentric model of the universe, meaning Earth-centered. He also offered detailed mathematical rules describing the motion of each of the other planets. This brings us to 2 different models of the universe. The geocentric, where the Earth is at the center of the universe and all heavenly bodies, all other celestial objects, move around the Earth, or the heliocentric, where the sun is at the center of the universe and all heavenly bodies move around the sun including the Earth. Nicholas Copernicus was a Polish astronomer and mathematician who came up with the heliocentric model of the universe, which came to be factual. He began this work in 1514, the 16th century, and it was a handwritten notebook of observations in which Copernicus laid out the foundations of this heliocentric model. He didn't sign his work and distributed it only to a few friends because this was very controversial at the time. The heliocentric model went against the teachings of the Catholic Church, which said the geocentric model with the Earth at the center of the known universe was the only possible way that the heavens were constructed. The heliocentric model flew in the face of that. Tycho Brahe, known mainly by Tycho, was a Danish astronomer, and although his theories were ultimately wrong, he's incredibly important because the amount of data, of astronomical data he collected was incredibly accurate. So he had great methods for collecting data on the solar system, on the Earth, and on the sun and the moon and the other celestial bodies that he could see. The mathematics with which he came up with gathering all this data was correct. It was his observations about the data that were wrong. Tycho argued that the moon and the sun revolved around the Earth, while other planets revolved around the sun, which, when you try to put both of those theories together, it doesn't really make a lot of sense. So this was a theory system that he developed that was different from the geocentric model proposed by Ptolemy and the heliocentric model proposed by Copernicus. Johannes Kepler, a German astronomer and mathematician, was a student of Tycho's, but he didn't agree with Tycho's interpretation of the data, and he also disagreed with Copernicus, claiming that the other bodies in our solar system moved in an elliptical motion and not a circular motion that Copernicus thought. So Copernicus provided this base model, and Tycho provided the base data for Kepler's theories. Um, as a student of Tycho, he studied his teacher's works as well as the writings of Copernicus. And it was this interpretation of Tycho's data using Copernicus's theories of a heliocentric model which allowed Kepler to propose the three laws of planetary motion. And those three laws are the law of ellipsis, asserts that planets orbit the sun elliptically, like in oval patterns. This law explained why theories that claimed the planets orbited the sun or earth in circular patterns were inconsistent with observed data. The second law was the law of equal areas that stated the speed of planetary motion changes constantly depending on the distance of that celestial object from the sun. And the third law of planetary motion was the law of harmonies. This compared the movement of all the planets, claiming a similarity in their motion, using ratios and claiming that the similarity is based on the gravity within the galaxy itself. This leads us to Italian mathematician and astronomer Galileo Galilei, considered by many to be the father of modern science. He's also considered to be the father of modern physics and astronomy. He created several different telescopes, improving the power of with each successive model, and used them to record extraordinary amounts of data. His interpretations of the data yielded some remarkable discoveries, including truths that the stars were further away than planets, that there were mountains on the surface of the moon, that Jupiter at the time observable had 4 moons, and that Saturn had a set of concentric rings around it. He eventually compiled and published his observations in a 1610 work called The Starry Messenger. Galileo's work, combined with previous discoveries of Copernicus and Kepler, left little doubt among the mainstream scientific community that the Ptolemaic model of the universe, the geocentric model, was incorrect. He also conducted a famous experiment in which he showed Aristotle had been mistaken in his assumption that objects of different weights falling at different rates of speed. Having proven this, he went on to establish an explanation of speed and motion. Galileo also created a thermometer, which permitted more accurate data collection on human beings. Galileo's theories and writings were in direct contradiction to the Catholic Church, whose feelings of a geocentric model with Earth at the center of creation, Earth as the center of the known universe, um, didn't fit with scientific data and scientific fact. So the church felt it easier to condemn Galileo and the heliocentric conceptions of the universe rather than make it fit into their religious framework. In 1632, Galileo was referred by the Pope to the Roman Inquisition, who would study his works to see if they were products of heretical teachings, see if they were hearsay, going against the Word of God, and more importantly, against the Word of the Catholic Church. Galileo's trial in 1633 found that his works did go against the teachings of the Catholic Church and against God himself, and so he was ordered to recant all of his work and put under house arrest. This was an incredibly dangerous precedent of the Catholic Church and the Pope himself overstepping science and fact based on tradition and religious beliefs. Although Galileo continued to write and research and publish, this had a devastating effect on the scientific community at the time. Using the works of Copernicus and Kepler and Galileo before him, Sir Isaac Newton, the English astronomer, physicist, and mathematician, was able to condense and synthesize all of the previous done work and present this as a foundation for new theories on gravity and motion. In his work, The Principia, the most influential science book ever written, this presented a new view of the world, one expressed in entirely mechanical terms, with Newton portraying the universe as a large clock that operated by a consistent set of rules. The book was well received by the academic community of Europe at the time, and this new world view became the accepted paradigm until the atomic age. Newton's laws of motion are the first law is the law of inertia, argues that bodies in motion tend to stay in motion unless acted on by an outside force. This force can be something viable and obvious or something more subtle, like gravity. Newton's second law of motion, the fundamental law of dynamics, explains how the velocities of objects change when outside forces are applied. This is considered the most important of the three laws of motion. And Newton's third law of motion, the law of reciprocal actions, posits that for every action there is an equal and opposite reaction. The central unifying element for Newton was that motion in the heavens was linked to motion on Earth by the law of universal gravity. Before the scientific revolution, many practitioners of medicine relied on theories that were centuries old and rarely based on anatomical research or observation. Medical treatments were at best ineffective and at worst lethal. In addition, the church banned dissection, a practice critical in understanding the human body and how illnesses affected it. In general, the church viewed sickness not so much as a physical disorder, but as a spiritual punishment for sin. Correspondingly, human intervention was seen as challenging the will of God. During the Middle Ages, the Catholic Church assumed responsibility for taking care of the poor and the sick. Consequently, the Church also became the acknowledged authority on which medical practices were acceptable. Many lower ranking clerics took on physician like roles, since they were usually the ones charged with directly dealing with the sick. Church leadership was uncomfortable with this development because clerics who practiced medicine tended to shirk their religious duties. The church began to pass canon laws that both regulated and limited the involvement of clergy in the practice of medicine. Eventually, with the rise of universities and colleges, trained physicians began to replace clerical physicians. William Harvey was an English physician who wrote On the Movement of the Heart and Blood in Animals, a work based on years of observation and dissection of both animal and human subjects. In the book, Harvey argued that blood was pumped through the body by the heart and constantly circulated. He also proved that the same blood flows in both veins and arteries. Harvey's conclusions and theories created a basic model of blood circulation that is still recognized as the standard today. Carolus Linnaeus was a Swedish botanist who helped develop a system for the classification and formal naming of all plants and animals on Earth by genus and species. And this naming system is still in use today. He also conducted research into hybridization, the process by which two distinct species are crossbred. Long before Charles Darwin pioneered his theories of evolution, Jean-Baptiste Lamarck, a French biologist, had an early theory of evolution, and he published this in his famous works, Philosophie zoologique. This proposed the early theory of evolution where he laid out two laws. The first stated that changes in an animal or plant's environment can cause modifications in behavior, which in turn can lead that animal or plant to either make greater or less use of a certain body part or structure. So environmental changes affect animals and plants physically. The second is that changes to the body or structures of an animal or a plant are passed down to their offspring or children and passed down throughout generations. During the scientific revolution, the field of mathematics was changed dramatically. The modern signs for mathematical operations were created by Francois Vieta in France in 1603 and were adopted as a standard during the scientific revolution. In addition, new branches of mathematics arose. René Descartes came up with analytical geometry, and Sir Isaac Newton invented calculus, the study of rates of change. Other notable inventions during the scientific revolution were the telescope, invented in the Netherlands in the late 16th century. Until Galileo made improvements to it in the early 1600s, it had not been widely used as a practical tool for scientific observation. Sir Isaac Newton made further refinements in the early 1700s when he invented the reflector telescope, which uses a curved mirror to magnify objects to a much greater degree than a simple glass lens. The reflector telescopes are still in use today. Microscopes were another invention of the scientific revolution that are still prominently used today. The first simple microscopes, appeared during the Renaissance, but were limited in power and the range of tasks that they could be used for. In 1590, Dutch spectacle makers or eyeglass makers Hans Janssen and his son Zacharias began to construct compound microscopes where they used several lenses to produce greater magnification. In the mid 1600s, another Dutchman named Anton van Leeuwenhoek developed new methods for grinding and polishing tiny lenses of great curvature, which gave magnifications up to 270 diameters, the finest known at the time. He used these lenses to build much improved microscopes and make groundbreaking observations. For instance, he was the first to see bacteria and blood corpuscles and the life found in a drop of water. In the 1660s, Robert Hooke of the Royal Society of London improved even further, and his microscopes were able to perform a series of weekly demonstrations that showed the power of the instrument. In 1665, he wrote Micrographia, a finely illustrated compendium of microscopic observations that also used the word cell as a biological term for the first time. And this sparked public interest in microscopy as a field of science. Another invention during the scientific revolution was the pendulum clock, invented by Christian Huygens, a 17th century Dutch scientist. This allowed scientists to more accurately measure time. Galileo himself actually had a design for a pendulum clock in the late 1500s, but never built it. Huygens' prime innovation was the balance wheel and spring, which allowed clocks of the era to keep time accurate up to 10 seconds. Watches and clocks were built in all sorts of shapes and sizes, usually using this pendulum concept, including portable devices that allowed scientists to record time accurately during their experiments. The basis and foundation for the technological achievements in computers we have now in the 21st century started back during the scientific revolution with the inventions of mechanical calculators. First invented by Wilhelm Schickard, a 17th century German inventor. Schickard corresponded with Kepler in the late 1620s and described a design he had for a calculating clock that could perform complex numerical calculations. His machine could add, subtract, multiply, and divide. Later on in the 17th century, Schickard's model and one created by French mathematician Pascal were used to create a step reckoner that could also do square roots. These were the basis and foundations for modern computers, which can do a variety of calculations in a fraction of the time. What was the significance of the scientific revolution? Well, the most obvious result of the scientific revolution was the rejection of ancient and medieval systems in science, astronomy, and medicine. After the scientific revolution, many previously accepted theories had been completely disproved or discarded. The methods developed during the scientific revolution would fuel discoveries for centuries to come. Basing science more firmly in empiricism made conclusions more consistent, reproducible, and accurate. The scientific revolution also set the stage for the Enlightenment. Like the pioneers of the scientific revolution, Enlightenment thinkers strove to make conclusions based on observation, logic, and reason rather than on faith. Though the scientific revolution had little immediate impact on society as a whole, its long-term repercussions can still be felt today. Perhaps more important than the specific advances in science, the revolution represented a shift in worldview. It was an intellectual revolution that changed the way the people saw and interpreted the world around them.